Welcome, everyone. Today, we are going to explore the wonderful world of set operations. If you are an absolute beginner, you are in exactly the right place. We're going to look at how we can combine and compare sets in mathematics. To make this really intuitive, I want you to think of sets simply as bags of objects. A set is just a bag, and the items inside are its elements. When we talk about set operations, we are really just talking about different ways to combine or compare the contents of these bags. We'll be learning about several operations today: union, intersection, difference, complement, symmetric difference, and the Cartesian product. Don't worry about the formal names or the symbols right now. We'll walk through each one step by step. Before we dive into the operations, let's do a very quick recap and set up our roadmap. Remember our core idea. A set is like a bag. In math, a set is just a collection of distinct objects, which we call elements, and we usually write them inside curly braces. Throughout today's lesson, we're going to use two specific bags, or sets, as our running examples. Let's call the first bag A. Set A contains the numbers 1, 2, 3, and 4. Our second bag, set B, contains the numbers 3, 4, 5, and 6. If you look closely at these two bags, you'll notice that they share the numbers 3 and 4. This overlap is going to be the key to understanding most of our operations. Here's a quick look at what we'll study today. We'll look at the union, which is everything in bag A or bag B. We'll look at the intersection, which is only what's in both bags. We'll explore the difference, which is what is in A but not in B. We'll look at the complement, which is everything outside of our set. Then we'll cover the symmetric difference for items in one bag but not both. And finally, the Cartesian product, which pairs things up. One quick rule before we start. Whenever we talk about the complement, meaning everything not in a set, we must always define a universal set, which we call U. You can't really know what is outside a bag unless you know the size of the room the bag is sitting in. All right, let's start with our very first operation, the union. We write this with a symbol that looks like a giant capital letter U. The union of sets A and B simply means everything in bag A or bag B. Formally, A union B is the set of all elements that belong to A or belong to B or belong to both. A great way to visualize this is to imagine taking bag A and bag B and pouring all of their contents into one big bowl. Let's look at our example. Set A has 1, 2, 3, and 4. Set B has 3, 4, 5, and 6. When we pour them together, our new set, A union B, contains 1, 2, 3, 4, 5, and 6. Now, you might notice something important here. The numbers 3 and 4 were in both bags, but when we write out our final union set, we only list the 3 and the 4 once. In set theory, we don't keep duplicates. An item is either in the bag or it isn't. Looking at the membership rule, we can say an element X is in A union B if and only if it is in A, or it is in B, or it is in both. If you look at the Venn diagram, the union is that entire shaded area covering both circles completely. Next, let's look at the intersection. The symbol for intersection looks like an upside-down U. While the union was about bringing everything together, the intersection is much stricter. It only wants what is in both bags. By definition, A intersection B is the set of elements that belong to A and belong to B at the exact same time. Think of it as finding the items that both bags have in common. Let's bring back our two sets. Set A is 1, 2, 3, 4. Set B is 3, 4, 5, and 6. What numbers appear in both lists? Only the 3 and the 4. So A intersection B is simply the set containing 3 and 4. If we look at the logical rule for this, an element X is in A intersection B if and only if it is in set A and it is also in set B. In our Venn diagram, this is beautifully represented by that overlapping middle section where the two circles cross. That shared space is our intersection. Now, what happens if we try to find the intersection of two sets that have absolutely nothing in common? This brings us to a special case known as disjoint sets. Two sets are called disjoint if they share no elements at all. Let's look at a new example to see this in action. Let's say set A has the numbers 1, 2, and 3. And let's say set B has the numbers 7, 8, and 9. If we ask, what numbers do these two sets share? The answer is, well, nothing. There are no common items. In mathematics, we represent this nothing with a special concept called the empty set, which we write as a circle with a slash through it. So we say A intersection B equals the empty set. If you look at the Venn diagram for disjoint sets, it makes perfect visual sense. The circle for A and the circle for B are drawn completely apart. They do not overlap at all. It's worth taking a moment to appreciate the empty set. It's a set with absolutely no elements, literally an empty bag, which we can write as just an open and closed curly brace with nothing inside. It's a perfectly valid set. In fact, every set contains the empty set as a subset. Because the empty set has no elements, it can't possibly violate the rules of being a subset. We are now moving on to a very interesting concept called set difference, which we write as a backslash, in B. You can read this simply as A minus B. The set difference contains all the elements that are in set A, but with anything that also belongs to set B completely removed. To visualize this, think of our bag analogy. Start by holding bag A. Now look inside bag B. If you see any items in your bag A that are also sitting inside bag B, you throw those items away. Whatever's left in your hands is the set difference. Let us look at our standard example. Set A contains the numbers 1, 2, 3, and 4. Set B contains the numbers 3, 4, 5, and 6. If we want to find A minus B, we start with the contents of A, 1, 2, 3, and 4. Now we check set B. We notice that the numbers 3 and 4 are in set B as well, so we must remove them from our collection. What are we left with? Just 1 and 2. Therefore, the set difference, A minus B, equals the set containing 1 and 2. We kept 1 and 2 because they are only in A. We removed 3 and 4 because they are in both. If you look at the Venn diagram on the right, this concept becomes beautifully clear. We have our two overlapping circles for A and B. The only part that is shaded is the left side of circle A, the crescent shape. The overlapping middle section is empty, and circle B is entirely empty. This shows we only want the pure, unshared part of A. Now, an incredibly important rule to remember here is that order matters. Subtraction in sets is not symmetric. This is just like regular math, where 5 minus 3 does not equal 3 minus 5. Let us prove why order matters by moving to the next slide and switching the bags around. Let's look at B minus A. By switching the letters, the question we are asking changes completely. B minus A asks, what is in bag B but not in bag A? Following our rule, we now start with bag B, and we will remove anything we find that also belongs to set A. Our sets are the same. Set A is 1, 2, 3, 4, and set B is 3, 4, 5, 6. This time, we start holding set B, 3, 4, 5, and 6. We look over at set A and see it contains 3 and 4, so we must remove 3 and 4 from our back. We're left with 5 and 6. Therefore, B minus A equals the set containing 5 and 6. Let us compare the results side by side. The expression A minus B gave us the result 1, 2, but the expression B minus A gave us the result 5, 6. Looking at the Venn diagram for B minus A, you can see that now only the right-hand crescent is shaded. The overlap is empty, and circle A is empty. We are left with only the pure, unshared part of circle B. Our conclusion is very clear. A minus B does not equal B minus A in general. Whenever you are doing set difference, pay very close attention to the order of the bags.
Now, let us move on to a new operation called the complement. We write this as the letter A with a small lowercase c floating at the top right like an exponent. The complement of A is beautifully simple. It is everything that is not in A. Specifically, the complement of A is every element in the entire universe, which we call U, that does not belong to set A. Think of the complement as the outside of bag A, but still within the walls of your classroom, which represents the universe. Let us look at an example. First, we must define our universe, U. Let us say U is the set of numbers 1, 2, 3, 4, 5, and 6. Now, let us say set A is the set containing 1, 2, and 3. To find the complement, A to the C, we simply look at our universe and cross out anything that is in A. We cross out 1, 2, and 3. What is left? The numbers 4, 5, and 6. So the complement of A is the set 4, 5, 6. Take a look at the Venn diagram. We have a large purple rectangle representing our universe, U. Inside it is a white circle representing set A, holding the numbers 1, 2, and 3. Notice where the shading is. The entire rectangle outside of circle A is shaded purple, and that's where the numbers 4, 5, and 6 live. It is very important to understand that the complement depends entirely on what U is. If you change your universe, your complement changes too. There are two very useful laws to remember about complements. First, A union A complement equals U. If you take bag A and combine it with everything that is not in bag A, together they cover the entire universe. Second, A intersection A complement equals the empty set. A bag cannot share any items with the things outside of the bag. There is zero overlap. Moving smoothly along, let us look at a combination of what we have learned, called the symmetric difference. The symbol for this is a triangle, written as A triangle B. The symmetric difference contains elements that are in exactly one of the bags, A or B, but absolutely not in both. Think of these as your exclusive items. These are things that are completely loyal to only one bag. Let us use our standard sets again. Set A is 1, 2, 3, 4. Set B is 3, 4, 5, 6. We know that 3 and 4 are in both bags. Because they are shared, we exclude them. We only want the items that appear in one place. From set A, we keep 1 and 2. From set B, we keep 5 and 6. So the symmetric difference, A triangle B, is the set 1, 2, 5, 6. The Venn diagram paints a perfect picture of this. Look at the two circles. The left crescent is shaded, the right crescent is shaded, but the overlapping middle section, the intersection, is completely empty. There is a great alternative formula for this that uses the operations we already know. The symmetric difference of A and B is equal to A minus B unioned with B minus A. In plain English, this just means you take the items exclusive to A and you add them together with the items exclusive to B. Finally, for this section, let us explore the Cartesian product, written as A times B. This operation is a little different. A times B creates a set of all possible ordered pairs. We write an ordered pair inside parentheses with a comma between them, like A, comma B. In these pairs, the first item always comes from set A and the second item always comes from set B. Think of it like getting dressed in the morning. If set A is every shirt you own and set B is every pair of trousers you own, the Cartesian product is every possible outfit combination you can make. Let us look at a simple example. Set A contains the numbers 1 and 2. Set B contains the letters X, Y, and Z. To find A times B, we systematically pair them up. We take the number 1 from set A and pair it with every letter in B. This gives us the pair 1, X, the pair 1, Y, and the pair 1, Z. Now we move to the number 2 in set A and do the same thing. This gives us 2, X, 2, Y, and 2, Z. So our final set for A times B contains those 6 distinct pairs. Notice that these elements are ordered pairs now, not single objects. The first slot must be from A, the second slot must be from B. Order matters immensely here. The pair 1, X is not the same as the pair X, 1. If you look at the diagram on the right, you can see a visual map of this. Set A is listed vertically on the left with 1 and 2. Set B is listed horizontally across the top with X, Y, and Z. Where they meet on the grid, we form our pairs, creating a nice rectangle of 6 combinations. There's a very handy formula to figure out how many pairs you'll get. The size of A times B is equal to the size of A multiplied by the size of B. In our example, set A has 2 elements, set B has 3 elements. 2 times 3 equals 6 total pairs.
Welcome back. Now that we have a good visual understanding of sets acting like bags of objects, we are going to look at set operations from a slightly different, more precise perspective. We are going to use logic. You might ask, why use logic? Well, set operations can be defined absolutely precisely using just 3 basic logical symbols. Once we know these symbols, we can write a single one-line definition for every set operation we've learned, without needing to draw any Venn diagrams at all. Let's take a look at the logical connectives we will use. We have a table here with the symbols, their names, their meanings, and a quick everyday example. The first symbol is a little V shape. This is the logical OR. This statement is true when at least one side of it is true. For example, if I say it is raining or cold, that statement is true if it's just raining, if it's just cold, or if it's both raining and cold. The second symbol looks like an upside-down V or a little tent. This is the logical AND. This is much stricter. It is true only when both sides are true at the exact same time. If I say it is raining and cold, both of those conditions must be happening for my statement to be true. The third symbol is a small horizontal line with a downward hook at the end. This is the logical NOT. Its job is very simple. It flips true to false and false to true. So not raining is true only when it is actually not raining. Finally, we have a symbol that looks like a backward capital E. This means there exists. It simply means that at least one element satisfies the condition we are looking for. For example, we can write, there exists an X such that X is an element of A. Notice our color key on the bottom left. These logical symbols perfectly mirror our set operations. The pink logical OR matches the pink union. The teal logical AND matches the teal intersection, and the purple logical NOT matches the purple complement. To use these logical symbols, we will follow a specific pattern. We will fix a universal set called U. Then we will sweep through every single element X inside that universe. For every element, we will ask a question. Is X in the result? To answer this, we check if X satisfies a specific logical condition. We will build a membership evaluation table for this. Each row of the table will correspond to one element of the universe, and we will test its truth values to see if it makes it into our final set. Let's see this in action with the logical definition of union. The formal definition is written as X is an element of A union B, if and only if X is an element of A or X is an element of B. Notice we use that logical V symbol for OR. In plain English, the process works like this. Pick any object X from the universe. Ask yourself, is X in bag A? Then ask, is X in bag B? If either answer is yes, or if both answers are yes, then that object X goes into the union. Remember, this is an inclusive OR, so belonging to both sets is perfectly fine. This connects beautifully to our Venn diagrams. The shaded region of a union covers everything in the left circle, the right circle, or the overlap in the middle. This is exactly what the logical OR produces. Let's trace this through our evaluation table. Our universe, U, contains the numbers 1 through 7. Set A is exactly 1, 2, 3, and 4. Set B is 3, 4, 5, and 6. We sweep through the universe one number at a time. Look at row 1. Is 1 in A? True. Is 1 in B? False. Since we are using OR, we just need one true. So is it in the union? Yes. Look at row 3. Is 3 in A? True. Is 3 in B? True.
True or true is still true, so yes, it is in the union. Look at row 5. Is 5 in A? False. Is 5 in B? True. We have one true, so yes, it is in the union. Now pay close attention to row 7. The number 7 is in our universe, but it is neither in A nor in B. Because both conditions are false, the logical OR gives us a false, so 7 is correctly excluded. Our final result for A union B is the set 1, 2, 3, 4, 5, 6. Now let's move to the logical definition of intersection. The formal definition states that X is an element of A intersection B if and only if X is an element of A and X is an element of B. Here we use the little tent symbol for AND. In plain English, pick any object X from the universe. Ask if X is in A, then ask, is X in B? Only if both answers are yes is X allowed into the intersection. If you get even one no, that is enough to exclude the object. This means the logical AND is much stricter than the logical OR. Every element of the intersection is automatically in the union, but not the other way around. The intersection of A and B is always a subset of the union of A and B. Let's look at the exact same sets in our table, but this time applying the logical AND. Look at row 1. It is in A, but it is false that it is in B. Because we need both, the result is no. Row 2 is also a no. But look at row 3. Is 3 in A? True. Is 3 in B? True. Because both are true, the AND condition is met, so yes, 3 is in the intersection. The same happens for row 4. Notice row 7 again. 7 is in the universe, but in neither set. The AND condition immediately gives a false, so it is correctly excluded. Our final result for A intersection B is just the set containing 3 and 4. Next, we have the logical definition of set difference, A minus B. The formal definition is X is an element of A minus B if and only if X is an element of A and not X is an element of B. We can also write this a bit simpler using the not an element of symbol. We can write X is an element of A and X is not an element of B. In plain English, X must be in A, that has to be a yes, and X must not be in B, that has to be a no. Both of these conditions must hold simultaneously. Let's look at the table. Our universe, set A, and set B are exactly the same. But notice the third column is now asking, is X not in B? Let's evaluate row 1. Is 1 in A? True. Is 1 not in B? True. It is not in B. True and true means yes, 1 is in the set difference. The same is true for number 2. Now look at row 3. Is 3 in A? True. Is 3 not in B? False, because 3 actually is in B. Since we have a false, the AND condition fails, so no, 3 is not in the set difference. Let's skip down to row 7. Is 7 in A? False. Because it's an AND condition, it doesn't even matter what the second column says. 7 is not in A, so it fails immediately. It is correctly excluded, even though it is also not in B. Our final result for A minus B is simply the set containing 1 and 2. Finally, let's explore the logical definition of set complement. The formal definition is X is an element of A complement if and only if X is an element of the universe U and X is not an element of A. When we are working inside a fixed universe, we already assume every X we look at is in U, so we can safely abbreviate it to simply X is not an element of A. In plain English, we are just flipping the membership of every element. If you are inside bag A, then you are not in A complement. If you are outside bag A, but still inside the universe, then yes, you are in A complement. The logical not is the simplest operation. It uses just one symbol and performs a total flip. There's also a neat rule here called the double complement. In logic, if you say not P, it just means P. In sets, if you take the complement of A and then take the complement of that, it brings you right back to the original set A. Let's look at our table. Note that we have changed our sets for this example. The universe U is now just the numbers 1 through 6. Set A is the numbers 1, 2, and 3. We sweep through our universe. Row 1 is 1 in A? True. So is it not in A? False. Therefore, it is a no for the complement. This happens for 1, 2, and 3. Now look at row 5. Is 5 in A? False. So is it not in A? True. It gets flipped. So yes, 5 is in the complement. The same flip happens for 6 and 7. It is very important to remember that not doesn't simply flip every answer in the whole world. Only elements within our defined universe U are candidates. Nothing outside U can ever enter A complement. Our final result for A complement is the set containing 4, 5, and 6.
Let us take a deep breath and gently move forward to the logical definition of the symmetric difference represented by the triangle symbol. So we say A symmetric difference B. If you look at the top left of the slide under formal definition, you will see a slightly longer mathematical statement. It reads, an element X belongs to A symmetric difference B if and only if we have a combination of two conditions. First, in brackets, X belongs to A or X belongs to B. Then we have an AND symbol, followed by a NOT symbol, and then our second bracketed condition, X belongs to A and X belongs to B. In plain English, this is simply saying or, but not and. Let's break down those bullet points. It means that X is in at least one of the bags, A or B, that is the OR part, but X is not in both bags simultaneously, that is the not and part. In logic, this precise condition is exactly what we call the exclusive OR, often abbreviated as XOR. Moving down to the dark blue box, we have an equivalent formula. We can write A symmetric difference B as the union of two separate differences, A minus B, union B minus A. In words, this means the elements that are exclusively in A and not in B, or the elements that are exclusively in B and not in A. Beneath this, there's a helpful note about the symbol for exclusive OR, which is a plus sign inside a circle. We read P exclusive OR Q as being true when exactly one of P or Q is true. It is false when both are true or when both are false. It strictly demands exactly one. Now, let us apply this to our sweeping truth table on the right side of the slide. We are going to test every element X in our universal set U, which contains the numbers 1, 2, 3, 4, 5, 6, and 7. Our set A contains 1, 2, 3, and 4. Our set B contains 3, 4, 5, and 6. Our table has columns for the element X from the universe, whether it is in A, whether it is in B, the result of our XOR logic, and finally, whether it makes it into the symmetric difference. Let us sweep through the numbers slowly. For the number 1, is it in A? True. Is it in B? False. True XOR false gives us true. So yes, 1 is in the symmetric difference. For the number 2, true for A, false for B. Again, exactly 1 is true. The XOR is true. Yes, 2 is in. Now look at number 3. It is true for A and true for B. Because both are true, the exclusive OR condition fails. It returns false. So no, 3 is not included. Number 4 is exactly the same. True for A, true for B. The XOR is false. No, it is excluded. Moving to number 5, false for A, true for B, exactly 1 is true, so the XOR returns true. Yes, 5 is in.
Number 6 is the same. False for A, true for B. XOR is true. Yes, 6 is in. Finally, let us look at number 7. Number 7 is false for A and false for B. As the text below the table explains, false XOR false is false. Because it is not in either set, it is correctly excluded. Therefore, our final result for A symmetric difference B is the set containing the numbers 1, 2, 5, and 6. Let us slowly transition to our next slide, which covers the logical definition of the Cartesian product written as A cross B. Under the formal definition, you will notice something different right away. We are no longer looking at a single element x. We are looking at a pair of elements, enclosed in parentheses, written as A comma B. The definition states the ordered pair A comma B belongs to the set A cross B if and only if A belongs to A and B belongs to B. There's a notice section below this with 4 important bullet points to keep in mind. First, the elements we are working with are ordered pairs, not single individual objects. Second, the first slot of the pair must always come from the first set, A, and the second slot must always come from the second set, B. Third, a pair is only in the final product if and only if both individual membership conditions hold true. And fourth, order absolutely matters. The pair 1, x is not the same as the pair x, 1. Below this, we ask the question, why and? Why is and the core logical connective here? Well, for a pair to qualify, both components must belong to their respective sets at the exact same time. Demanding 2 things happen together is exactly what the logical and requires. Let's test this on the right side of the slide. Here, our set A contains the numbers 1 and 2. Our set B contains the letters X and Y. Let us look at the table testing candidate pairs. The columns check the pair, whether the first item A is in set A, whether the second item B is in set B, the result of joining them with and the final yes or no result. Let us look at the first 4 rows. For the pair 1, x, 1 is in A, which is true. X is in B, which is true. True and true gives us true. So yes, it is in the product. For the pair 1, y, true and true gives us true. Yes. For the pair 2, x, true and true gives us true. Yes. For the pair 2, y, true and true gives us true. Yes. But now look at the last 2 shaded rows. These are candidate pairs that fail. Take the pair 3, x. Is 3 in A? No, that's false. Is X in B? Yes, that's true. But false and true evaluates to false. So no, this pair is excluded. Next is the pair 1, z. Is 1 in A? Yes, true. Is Z in B? No, false. True and false evaluates to false. No, it is excluded. As the text below the table confirms, 3 does not belong to A and Z does not belong to B, so the AND condition fails and those pairs do not make it into the final Cartesian product. Take a nice deep breath. Let us move to our final slide for this section, all logical definitions at a glance. This slide elegantly brings everything we've learned together into one unified picture. At the very top, in the dark blue box, we review the unified pattern over a universal set U. Every logical definition we've discussed follows the exact same form. We fix a universe U and check every element X inside it. The form is simply X belongs to the result if and only if some logical condition involving X belonging to A and or B is met. The truth table sweeps through the universe, dedicating one row per element. And the beauty of this system is that elements completely outside both A and B are tested too, and the logic correctly excludes them. Below this is a beautifully organized summary table. Let us read through it, connecting the set operation to its core logic. The union of A and B is defined by the logic X is in A or X is in B. The core connective is OR. The intersection of A and B is defined by X is in A and X is in B. The core connective is AND. The difference of A minus B is defined by X is in A and X is not in B. The core connective is AND plus NOT. The complement of A is defined by X is in the universe and X is not in A. The core connective is NOT. The symmetric difference of A and B is defined by X is in A exclusive OR X is in B. The core connective is XOR. And finally, the Cartesian product of A and B is defined by A is in A and B is in B. The core connective is AND. In the bottom left, we have the big takeaway. Set operations are truly just logical conditions wearing a disguise. Whenever you see a union, think OR. When you see intersection, think AND. Difference is AND NOT. Complement is simply NOT. Symmetric difference is exactly XOR. And the Cartesian product is an AND condition applied across two different coordinates.
Let's take a moment to pause and look at all the operations we've learned side by side at a single glance. At the top of our screen, we have our familiar example sets to guide us. Set A contains the elements 1, 2, 3, and 4. Set B contains 3, 4, 5, and 6. And our universal set, U, contains all the whole numbers from 1 through 7. Now, let's walk through the summary table together line by line. First is the union, written as A, the U-shaped union symbol, and B. The result is the set containing 1, 2, 3, 4, 5, and 6. In plain English, this operation gathers together everything in either bag. Next is the intersection, written with the upside-down U symbol. A intersection B results in the set containing just 3 and 4. As the plain English column tells us, this operation keeps only what is in both bags. Then we have set difference. A minus B, written with a backward slash, gives us the set containing 1 and 2. These are the elements that are in A, but not in B. Conversely, if we flip it to B minus A, the result is the set containing 5 and 6. These are the elements in B, but not in A. Notice how changing the order changes the result completely. After that is the complement, written as a capital A with a small lowercase c positioned like an exponent. The complement of A is the set containing 5, 6, and 7. In plain English, this represents everything in our universal set U that is not inside bag A. Finally, in our table, we have the symmetric difference, represented by a small triangle between the letters. A symmetric difference B gives us the set containing 1, 2, 5, and 6. In plain English, these are the elements found in exactly one of the two bags, leaving the overlapping elements out entirely. Now let's look at the bottom left of our screen. Here is a very useful formula for finding the size of the union, often called the Inclusion-Exclusion Principle. The vertical lines around the sets mean the size of, or the number of elements in. So the formula reads, the size of A union B equals the size of A plus the size of B minus the size of A intersection B. Why do we subtract? Well, when we add the total contents of both bags together, we end up counting the overlapping elements twice. Subtracting the intersection corrects this double counting. Looking at our example numbers below the formula, set A has 4 elements,
Set B has 4 elements, and their intersection has 2 elements. So 4 plus 4 minus 2 equals 6. And indeed, there are exactly 6 elements in our resulting union. Moving to the bottom right, there's another beautiful way to think about the union. The union of A and B can be broken down into 3 completely separate, disjoint regions. The formula shows that the union of A and B is made up of A minus B, which is the only A part, united with A intersection B, which is the both part, united with B minus A, which is the only B part. As the text at the bottom reminds us, these 3 parts perfectly piece together, and they never overlap. Now we arrive at a truly elegant mathematical concept, De Morgan's laws. These laws describe exactly how the complement operation interacts with unions and intersections. They might look a bit intimidating at first, but let's break them down slowly together. Let's look at the first law on the left side of the screen. It states that the complement of A union B, written with A union B inside parentheses and the little c on the outside, is exactly equal to the complement of A intersected with the complement of B. In words, the complement of a union equals the intersection of the complements. In plain English logic, saying not A or B is exactly the same as saying not A and not B. Notice how applying the complement to the individual sets flips the union symbol upside down into an intersection symbol. Just below that is the second law. It is the perfect mirror image of the first. It states that the complement of A intersection B is equal to the complement of A united with the complement of B. The text explains that the complement of an intersection equals the union of the complements. In plain English, saying not A and B is the exact same as saying not A or not B. Here, applying the complement flips the intersection symbol right side up into a union symbol. If this still feels a bit abstract, let's look at the everyday analogy on the right side of the screen. Let's imagine that set A represents the weather condition of raining, and set B represents the condition of cold. Applying Law 1, if I tell you it is not raining or cold, what does that actually mean for our weather? It means 2 things must be true simultaneously. It is not raining and it is not cold. The logical or becomes an and. Applying Law 2, what if I instead say it is not both raining and cold? This simply means we don't have both miserable conditions at the exact same time. Therefore, we can confidently deduce that it is not raining or it is not cold. It could be one or the other, but definitely not both. You might be asking, why do we care about these laws? As written at the bottom right of the screen, De Morgan's laws let us rewrite complicated set expressions into much simpler ones. They are absolutely foundational. You will see them used constantly if you study computer logic, programming, and even electronic circuit design. We have finally reached the end of our journey, so let's take a slow, careful look at what we've learned today. This summary screen holds all the core concepts we've explored. On the left side, we have a quick recap of all 6 set operations. First, A union B combines everything in A or B. Second, A intersection B strictly keeps only what is in both sets. Third, the set difference, A minus B, leaves us with elements in A but definitely not in B. Fourth, the complement, A to the power of C, contains all elements of the universal set U that live completely outside of A. Fifth, the symmetric difference, A triangle B, isolates the elements found in exactly one of the 2 bags, leaving the overlapping elements out entirely. And sixth, the Cartesian product, A cross B, creates a brand new set of all possible ordered pairs written as A comma B in parentheses. Now, let's shift our focus to the key fact to remember on the right side of the screen. These are the fundamental mathematical rules that govern how our sets behave. First is commutativity. This means the order doesn't matter for unions and intersections. A union B is exactly the same as B union A. Similarly, A intersection B is exactly the same as B intersection A. However, right below that, we're reminded that set difference is not commutative. A minus B is not equal to B minus A. The order of your bags here is incredibly important. Next is the inclusion-exclusion formula for counting elements. The size of A union B equals the size of A plus the size of B minus the size of A intersection B. Then we have the Cartesian size rule. To find the total number of ordered pairs in a Cartesian product, the size of A cross B simply equals the size of A multiplied by the size of B. And finally, we have our newly learned De Morgan's laws. De Morgan 1 reminds us that the complement of A union B in parentheses equals A complement intersected with B complement. And De Morgan 2 reminds us that the complement of A intersection B in parentheses equals A complement united with B complement. Take a deep breath. You now have an incredibly solid foundational understanding of set operations. Thank you for following along at this gentle pace and taking the time to truly master these concepts. Please consider liking, sharing, and subscribing to join our gentle community, and I would truly love to hear your wonderful thoughts in the comments below.